Hi everyone, today we're going to learn about properties of logarithms, but first we're going to start with a recap of what we know about logarithms right now. So to review, we're going to evaluate each of the following, and in doing that, we're going to get base to across the equal sign. So we're going to solve this. We're going to go 25 to the x power. So 25 to the x power equals 5. What our goal here is to try to get common bases so that we can set our exponents equal to each other. So rewriting 25 to the x power is going to be 5 squared to the x times x equals 5, and that's to the 1 power. And as you can see, the bases are now the same, so we can set our exponents equal to each other. So now we have 2x is equal to 1, or x is equal to 1/2. So that's what x is. Now, remember that at this point right here, you can also use the change of base formula, okay? And in that, if you were to use the change of base formula, and that's only if you're allowed a calculator. So if you're allowed a calculator, you can use the change of base formula to get the same answer, but a different way. So you would go bring that variable. If your variable is in the exponential place, the power, you're going to bring that out front, and so you're going to get x log 25 is equal to log of 5. X equals log 5 divided by log 25. And using your calculator, you will get 0.5 is your answer, which is the same as 1/2. For this problem here, we're going to just go 3 base to across the equal sign. So we have 3 to the x power is equal to 27. And I noticed that both 3 and 27 have powers of are bases of 3. So I can change 27 to a different base, and I can say this is 3 to the x power equals 3 to the 3rd power. You can always just go off to the side and go, okay, let's break 27 down to 3 times 9. And then 9 breaks down to 3 times 3, and so that's going to equal 3 to the 3rd power, and that's where I got that 27. So now the bases are the same. I can set my exponents equal to each other, and I'm done. Here we have 9 to the x power is equal to 81. So I actually have a couple choices on this problem. One option is to keep it as a 9 to the x power and change this to a 9 squared. Bases are the same, so x is equal to 2. Also, alternate way to do this problem, I could break this down even to 3s. And so 9 is actually 3 squared, and there's an x here, so 3 squared times x is equal to, and let's see, coming here, see this 81? So we just broke this down. Now we have 81. Well, that's 3 to the 4th power. And if my bases are the same, I can set my exponents equal to each other, and I get x is equal to 2. Same answer, different way I did that slightly. Remember, going back from this part right here, one other way to do this is 9 to the x power equals 81. Change of base formula, x log 9 is equal to log 81. So x is equal to log 81 divided by log of 9. And of course, I'm going to get 2 when I do that with my calculator. I don't have a calculator. If you don't have a calculator, you want to do it this way. If you're allowed a calculator, you have this option. Just remember, you may never cancel your logs, and you can never cancel these values here, 81 divided by, you do not do that. Okay, the next problem says 2 to the x power. So 2 to the x power equals 1 over 32. Rewriting 1 over 32 is going to give me 2 to the x power equals 1 over 2 to the 5th power. Remember, the bases have to be the same. So they have to be on the same playing field, the same level. So you're going to need to bring this 2 to the 5th power up top. And when doing that, you end up getting 2 to the x power equals 2 to the negative 5 power. Bases are the same. I can set my exponents equal to each other. Here we have base to across the equal sign. So we have 5 to the 3rd power is equal to x. So on this problem, we're not doing anything other than solving. I don't have to have the same base because it's already solved for x. So we just say x is equal to 5 times 5 times 5, which is 125. For this problem, we go 3 to the second power, so base to cross the equal sign equals x. And again, like the previous problem, we don't have to get a same base. We just say x is equal to 9 because we're just simplifying that one side. So graphing exploration, I would suggest that you take a minute and graph log of x, either in Desmos or by hand. We've done this problem a couple of times in different video series and perhaps in your classes too. Just keep in mind a couple of things. First of all, anytime you're graphing a log, your asymptotes are always vertical. You'll always have a vertical asymptote when you're graphing a logarithm. But if you're graphing an exponential equation, your asymptotes will always be horizontal. So a couple of things, if you don't have a calculator, let's say you didn't have Desmos calculator on the computer, or you didn't have that on your cell phone or mobile device, well, you could change this into an exponential equation, because we know that there's a little 10 down here, 10 base 10. Even though we don't see it, we know it's actually there. So you can rewrite this equation as 10 to the y power, see base to cross equal sign, is equal to x. And in this case, you would keep in mind that you're going to be plugging values in, but if your y is your exponent or your power, that's where you're going to plug values in. You're going to plug them in down here on the y side. So I'm always plugging in 0 and 1 for logarithms. Plugging in 0, 10 to the 0 power is 1. Plug in 1, 10 to the 1 power is 10. So I end up getting 1, 0, and I get 10, 1. And so my graph is going to look like this. It's going to come up and it's going to go like that. That's my logarithm graph. Okay, that's this graph over here. So here's your value 1, 0, and here's 10, 1. Now, keep in mind, how would I find the inverse function of this? Well, I have a couple of options. One option is to draw the line in, that I could draw this line, this y equals x line, right? And then I can reflect my graph across that x equals y axis, or y equals x, okay? Option 2 is I could take my points and take the inverse of my points. So if I have 1, 0, my inverse is going to be 0, 1. And if I have 10, 1, my inverse is going to be 1, 10. Okay, and so that's option 2, and I know that this graph is now going to come up like this. And the inverse of this graph, now do you remember how to find an inverse? If this is my equation here, I'm going to come down to this area here. If that's my inverse, I'm going to switch my x and y and solve for y. So now I have 10 to the x power equals y. It's already solved for y, so I don't have to do anything to that. So y equals 10 to the x, which is exponential, okay? And if y equals 10 to the x, and this is being exponential, then that means that my graph right here will actually have a horizontal asymptote going across. So on the next screen, I'm going to show you, this is my y equals 10 to the x, and you have a horizontal asymptote. This asymptote is at y equals 0. My domain for this graph, left to right, is going to be negative infinity to infinity, and my range is going to be low to high, so it's going to be not including 0 to infinity, positive infinity, because that's going to keep going up. For this graph, you are going to have so remember, this is a horizontal asymptote. This one's a vertical asymptote because it's a log graph. And so vertical asymptote here at x equals 0. For this value, my domain, left to right, is not including 0, goes 0 to infinity because it does go this way. My range is going to be low to high, so it's going to be negative infinity to positive infinity. Now, something to think about. If these are inverses of each other, which they are, okay, what I'd like you to consider is realizing that the domain for this equation is my range for that equation. My range for this equation is my domain for that equation. And that goes for all inverses, okay? Likewise, here's ln of x. So if I were to graph ln of x, and you didn't see that, well, you know what the ln of x's inverse is y is equal to e to the x power. Well, if that's the case, then e to the x is exponential, like if we plug in x and y. Now remember, if I have x up here, my values are going to be plugged in down here under the x. So we have 0. So if x is 0, y is 1. If x is 1, then y is e. And remember what e is. E is approximately 2.718 or so. So we have 0, 1, and then we have 1, e, okay, which is about 2.718. So my graph is exponential. It is going up like this. Now, to find the inverse of this, of course, I can flip my x and y. Another way is just to do this kind of thing, where you flip over the y equals x axis. I think the easiest thing for everybody to do is just to go, well, that's 0, 1, and this point is 1, comma e. Well, and e, remember, is 1, comma 2.718. If you flip the inverse, if you find the inverse of the points, instead of this being 0, 1, this will be 1, 0. And instead of this being 1, comma 2.718, it'll be 2.718, comma 1. And so this graph will do this. Okay? Again, your log equations or your natural log equations will always have a vertical asymptote. That will have a vertical asymptote, whereas your exponential equations will have a horizontal asymptote, and those asymptotes are at y equals 0, and your vertical asymptote starts at x equals 0. And I say starts at because basically it is x equals 0, but then when you make any kind of transformations, then that could change your asymptotes. They move with you. So again, we have our horizontal asymptote for our exponential equations. That's exponential. Anything's exponential if the variable is in the exponential place. If your power is your variable, then it's an exponential equation. For this one right here, and that's y is equal to 0. This right here is x is equal to 0. And so that's not exponential, but that's a logarithm. So that's going to have a vertical asymptote. Vertical asymptote at x equals 0. So here's a couple of transformations to do. And again, I would always start with the parent graph. You start with y equals log base 10 of x. We know what that looks like. We just did that. So when you're graphing this, the first thing we're going to do, and Kevin, make this a little bit bigger so you can see that, is you have your 2 points. Remember our points, we said 10 to the y power. And when we did that, our points were 1, 0 and 10, 1. So we know that this graph right now does this, okay? And it does have an asymptote right here at y equals 0, okay? And so, excuse me, that's x equals 0, okay? And that's my vertical asymptote. And now this value right here, this negative sign in front, what that does is it reflects across the x-axis, okay? So that means that this is still going to stay the same, this point, but this point, instead of being 10, 1, is now going to be 10, negative 1. It's not an inverse, it's a reflection. So reflections across the x-axis change the y term to a negative. Okay, so then now what we have is this. We have this value that looks like this graph. Okay, now that's what that does. This value here shifts my graph to the right or to the left. Okay, if it's plus 1, it's as if you would set that equal to 0, you get negative 1, so it's negative 1 to the left. So my new point is going to be at 1 to the left is at 0, 0, And 1 to the left here is 9, -1. So this graph now is going to do this. And this has also shifted my asymptote. And my asymptote, instead of it being x equals 0, is now at x equals over here at -1. Okay? So now we have this graph right here, which is y equals log base 2 of all that. And so what you're going to do for this is you're going to get and start with the parent function. But for this graph, we're going to graph this at an exponential. So 2 to the y power is equal to x. And I'm going to plot some points for x and y, but because y is my power, I'm going to plug in 0 and 1 for y. So 2 to the 0 power is 1. 2 to the 1 power is 2. So we have a little bit bigger. And making this a little bigger, what we now have is these 2 points. We've got the point at 1, 0. And then we have the point at 2, 1. It's a logarithm, remember? So this value here. Now, don't get this confused with this being an exponential equation. This is a logarithm because your x is not your variable. Your x is not your power. Okay, your logarithm or your exponential equations, you have x as your power. Now, with this graph, what we're going to do is we're going to there's no reflections, so usually do your reflections first. But what I'm going to do is move this. See this -3? I'm going to move my graph 3 units to the right. So that's going to move over. You need to be very careful with your graph because when you move your points out, when you move these over, your points should go with you. Okay, and so you of course would have to draw that, and then we're going to move this up 2, so up 2. So definitely when you're graphing your equations, right, you're going to have to be able to state a point. So make sure that when you move your values, that you move your values with you, your points with you. Graphing the function using transformations, we have f of x equals -e to the x minus 3. Remember what e is. E, we graphed this earlier in the lesson. So e is basically you have 0, 1, and you have 1e. And so this is my graph. It is exponential. My variable x is my power. The first thing you're going to do after you graph the parent function being e to the x power, is you're going to do its reflection. So that right here says reflect across the x-axis. Now, if it was e to the negative x, what that would do would be reflected across the y-axis. And instead of my graph doing this, it would actually do this. Okay, but they didn't ask that. So we're going to erase that. So what you're going to do now is we're going to reflect across the x-axis. And in doing that, here's my x-axis, right? So I'm going to reflect across that. So this is 0, 1. So now it's going to be 0, -1. And then this right here moves it to the right 3 places. And so, oops, I almost forgot this little graph right here. This being 1, this point being 1e, the next point is going to be 1 -e, because remember, you're still flipping it across the x-axis. So now it's doing this right here. I still need to move my graph 3 units to the right. So 1, 2, 3. So now I'm at 3, -1. See how I'm moving my point with me? And this value, the next point, which was, what was this? 1 -e, 1 -e. As I move it to the right 3 places, 1, 2, 3, that'll be 4 -e. Okay, so this graph is now going to look something like that. Okay, and it's going to go across, down like that. So when it's all said and done, now let's see here, it goes down. When it's all said and done, these are the steps. You've got y is equal to e to the x power. Notice your 1e and 0, 1. Reflect next. So now you have 0, -1, and you have 1 -e. Next step, last step, move it to the right 3 units. Shift all of your points that you have, call them critical points. Shift all of your critical points over to the right. Here's your 4 -e. Here's your 3, -1. If you need more than 2 points, then you can always plot more points. So now we're getting into the new lesson, which is log properties. So there are 3 log properties that we're going to discuss today. The first one is what we call the product rule. And what that basically means is that log base A of m times n is the same thing as log base A of m plus log base A of n. So this is actually pretty important. You can use this a lot of different ways. And what they're saying is this. They're basically saying log base A, and that A meaning any base of, let's say, 2. We're going to call it 2A. No, let's not call it 2A because we're already using A. Let's call it 2B, okay? So if I say log base A of 2B, all right, that's the same thing as breaking up this multiplication, and multiplication means add. So that's going to be log base A of 2 plus log base A of B. Okay. When would I use that? You would use that, and this, all of this is a proof here that you could look at more in depth, but you would use it, let's say I have log base 10 of, let's say, 15. Well, how could I rewrite that? Well, one way I could rewrite that is log base 10 of 5 times 3, right? Well, how could I rewrite that one more time? Well, I could say that that's log base 10 of 5 plus log base 10 of 3. And most of the time, you're going to want to prove that. So you're going to want to find out, well, what is log base 10 of 15? That's going to be a value. You can type that in your calculator. And then what they're going to do is they're going to say, well, if in fact 5 times 3 is 15, check, it is, and log base 10 of 5 plus log base 3 should equal whatever log base 10 of 15 is. So let's prove it. Let's prove this, something like this. So what we have is log base 10 of 27. And by the way, for these examples here, these are base 10, but they do not have to be base 10. You could have any of these bases, and this is going to, but the bases have to be the same. So we have log base 10 of 27. Well, in finding log base 10 of 27, it's actually, use your calculator, that's what it is, 1.4313. And by the way, you should verify this because there's going to be a lot of problems where if you can't plug this into your calculator, you get stuck on doing that, you're going to have a few problems trying to figure out or prove this when it comes time to do that. Well, if log base 27, when I use my calculator, log base 10 of 27 is 1.4313. Log base 9 is, and by the way, these are approximately, log base 9 is approximately 0.954, and log base 10 of 3 is approximately 0.477. So maybe you're asking me, well, why am I using those two values? Well, what they did was they said, well, log base 10 of 27 can be rewritten as log base 10 of 9 times log base 10 of 3. Well, or log of 3. Well, log base 10 of 9 times quantity 3 is going to give us this plus. Remember, multiplication, according to the product rule, in logarithm form, that multiplication becomes a sum, becomes addition. So now we have log base 10 of 9 plus log base 10 of 3. And that means that if in fact this is equal to this, and that value, log base 10 of 27 is 1.4313, then these two added together should be the same things. And that's 9.954 plus 0.477. And when I add these two values up, I in fact do get 1.4313. So you just have to add those up and plug those in, and that's what you should get. Now, these are approximations, of course, so their numbers might be off slightly, but that's what you're going to get. The next property is called the quotient rule. And it says that if I'm going to divide two values instead of like the multiplication, the product rule, when I multiplied, that was the same as addition. Whereas the quotient rule says if you divide, that's the same thing as subtracting. So basically, their concept is if you have log base, let's say 3 of 2 over 5, you can rewrite that as log base 3 of 2 minus log base 3 of 5. And then you're done. Unless you have a calculator and you can solve that's actually what they would be looking for. Now, occasionally you'll see other values where they give you the values of log base 3 and log base 3 of 2 and log base 3 of 5. But if they do that, then you plug those in. So take out your calculators, and if you were to plot this, okay, I'm not sure what happened with that. So if you were to plug these values in, so log of 12 over 7, I believe comes out to, if you were to plug that in your calculator, of 0.23408. Okay, so that's what this is right here. So if that's the case, and yes, you would use a parenthesis, so I'm trying to get that where you can still see the number. Here you go. Log base 12 is 1.079, let's say 18, or just 2. And log base 10 of 7 is 0.8451. Well, if this is the case, like what I told you on the previous slide, then log base 10 of 12 minus log base 10 of 7 should equal whatever log base 10 of 12 is, or should equal whatever log base 10 of 12 divided by 7 is. And so if that's the case, then 0.23408 should equal log base 10 of 12, which is 1.0792 minus 0.8451 or something like that. And so you're going to get super, super close because these are, again, approximations, but that's how you do that. The last rule is what we call the power rule, okay? And the power rule basically says that with your argument, remember M is your argument, if you have your argument as to a power, you can take that number and multiply it and put it up in front. So it becomes P log base A of M. Now, a lot of people might ask, well, why would we even want to do that? The reason why we would want to do that, because it does come in kind of handy when you see something like this. So if I were to rewrite, let's say, log base 10 of 2 to the 5th power, okay? Or even, let's even go before that. To the 5th power. Let's say 32, okay? And let's say that we had to rewrite that with just log base, with log of 2, like that. Well, in doing that, I would say, well, that's log base 10 of 2 to the 5th power. Well, in rewriting that, I would then say, well, if multiplication is addition, right? Isn't this the same thing? I'm going to put it over here as log base 10 of 2 plus log base 10 of 2 plus log base 10 of 2 plus log base 10 of 2. That's 4 of them. I need more space. Plus log base 10 of 2. Why couldn't I just take one of those and say, well, that's 5 times log base 10 of 2? Well, that's what we actually are doing, okay? We are actually going from this value here, let's see here, right here, and then we're going, okay, well, why can't I just take this 5 and bring it out front for right there and say, well, that's 5 times log base 10 of 2. And then that answer is the same as this answer. These two are the same, okay? So starting off, we are given log base 10 of 8 to the 5th power. So what I have is that log base 10 of 8 to the 5th power actually becomes 4.515, okay? And that's using a calculator. See this part, use your calculators. Now, to prove that, if I brought the 5 out front, see how that would be 5 times whatever log 8 is? Well, that would then give me 5 times 0.9031. Well, 5 times that is actually 4.515. So these are exactly the same. So we have a few problems here just to try to rewrite. We're not going to rewrite them too much, but we're going to just using properties of logarithms to simplify. We would get log base 3 of 9 plus log base 3 of 27, and then you would be done. However, this actually isn't even completely simplified. So let's go back and let's say, how many 3's do we actually have? We have 2 from this, right? 3 squared times 3 to the 3rd power. Well, isn't that keep the base, add the exponent? So really what I'm seeing is log base 3, which is this 3, of 3 to the 5th power, right? So really what this is saying is 5 times log base 3 of 3. Oh, what's this? 1. And so this would be 5 times 1, which, by the way, is 5. Woohoo. Okay, now this one right here, they're not all going to be that fun. This one right here, just rewrite it. You're going to have negative 3 times log base 8 of 11. Now this one, and that's your answer, by the way. We don't have a calculator, so that's what we get to write. For this one right here, for number C, let me see if I can move this over a little bit. Oh, good job. Okay, so we're going to just do these 2 problems here down lower. So this one right here, rewriting that's ln, natural log, of 4 to the 1/4 power. Well, remember, this right here, we're going to move that out front. So we have 1/4 ln to the 4th of 4, and then we're done. And this one right here, a division one, so we're going to use the division property. So that's going to be log base r of 9 minus log base r of 4, and that's what you get. Okay? Okay, so these ones we're going to rewrite as a sum or difference. So for this first problem, I'm going to start off rewriting that, and I'm going to say, well, that's starting off log base 4 of x squared plus, because remember multiplication here means addition. So we have plus log base 4 of y to the 5th power. But really, I can bring this 2 using the power rule. I can bring this 2 out front, and now I have 2 log base 4 of x plus 5 log base 4 of y. And that's my answer. And I can't simplify those any further. For this one right here, this might be a few steps, but let's use a different color. That's going to be log base 7, and we're going to use parentheses for this one, of x y to the 3rd power minus log base 7 of z squared. So we're going to start off like that. Well, from there, we actually see this multiplication in between here. See, there's a little multiplication here that we don't see, but we know it's there. And that's going to be, still, I'm going to keep that in parentheses for right now, log base 7 of x plus log base 7 of y to the 3rd power minus log base 7 of z squared. Now, you see now this we can't touch, but this one has a power rule. We're going to use the power rule to get that 3 out of the exponential power, and then this one also. So we end up getting log base 7 of x plus 3 log base 7 of y minus 2 log base 7 of z. And because all of those are different, this would be our final answer right here. Now, I can actually see maybe on a test or something like that, the question may be saying, well, log base 7 of x, we're going to call that a. And log base 7 of y, I'm going to call that b. And log base 7 of z, well, I'm going to call that c. And then given that information, I want you to rewrite this equation. So if that was the case, I would actually have log base 7 of x, a, plus, and if log base 7 of y is b, this would be 3b, minus, if log base 7 of z is c, then that would be 2c. So of course I changed the problem. I'm just saying if you end up getting this kind of thing, you can always plug values in and substitute that like that. Okay, so I'll move this over to the right a little bit. Let's finish this problem here. This says log base 10 of the fourth root of 7x cubed. So I'm going to rewrite that starting off as log base 10 of 7x to the third power, all to the 1/4 power. Now this becomes, see this 1/4 here? That's actually log base 10 of 7 to the 1/4, because I'm going to distribute that power. And see, there's a 1 here. So that's the 1/4 x to the 3/4 power. And so when I'm going to split these up because they are multiplying, and I'm going to use the product rule to do that. And I'm going to get log base 10 of 7 to the 1/4 power plus log base 10 of x to the 3/4 power. And finally, I have 1/4 log base 10 of 7 plus 3/4 log base 10 of x. And so that's actually my final answer there. Okay, so for these problems, what you're going to see is this. You're going to see a problem where you can't use your calculator and you're only given that log base 2 of 3 equals 1.5 and log base 2 of 7 is equal to 2.8. That's all you're given. That's the only information that you're allowed to use to find the answer to this problem. So you're going to have to somehow simplify each one of these values so that they reflect this here. So log base 2 of 21 is actually log base 2 of 3 times 7. Okay, and that's going to be log base 2 of 3 plus lots of 2. Log base 2 of 7. Excuse me. I'm going to move this down a little bit. And so then I know what log base 2 of 3 is. It's this value here. So it's 1.585 plus log base 2 of 7, which is 2.807. And just add those two up, and that's going to be your answer. For this one right here, we have log base 2 of 3, and because it's division, I'm going to use the quotient rule, so that's going to be minus log base 2 of 7. Well, log base 2 of 3 is 1.585, and log base 2 of 7 is 2.807, so you could just subtract those. Log base 2 of 49 is the same thing as saying log base 2 of 7 to the second power. Well, using the power rule, I'm going to move that 2 out front. So now I have 2 log base 2 of 7, which is 2 times 2.807. And then you can multiply those out to get the correct answer. And lastly, this is going to be log base 2 of 27, which we can't use because we can only use multiples of 3. We can only use 3 or 7. So that's going to be log base 2 of, let's say, 3 cubed. Okay, I'm going to still keep these in parentheses. Over 343, I believe, is 7 to the third power. So what I have here is, I don't know if you can see that. Let's see here. Is going to be log base 2 of 3 to the third power minus log base 2 of 7 to the third power. Well, we're going to use the power rule, and we're going to bring this 3 out front. So we're going to have 3 times log base 2 of 3 minus 3 times log base 2 of 7. Well, lucky us, we have these two values. So we can say 3 times 1.585 minus 3 times 2.807. And then you're going to get your answer once you use, multiply those out and subtract. I will caution that, again, these aren't the final answer. You do need to add those. And you do need to subtract number B, letter B, and multiply letter C. But if that's not your strong suit, you can always ask your teacher if you can use a 4-function calculator. And a 4-function calculator is just a calculator that has plus, minus, divide, and multiplication on it. And if that's something that you can use on your quiz or test or whatever that you have, then sometimes that's available too. Okay, more practice. We have log base A of 75, and so plus log base A of 2. So we're just going to simplify this into log base A of 75 times 2, which is 150. And then we're done. All they want us to do is simplify as a single log. So for this one right here, see this minus sign? So that's a big clue that I'm going to be using the quotient rule, where here I use the product rule, okay? That's the product rule. This is going to be the quotient rule. Okay, and in doing that, we're going to get, I'm going to start off rewriting this as log base A of x to the 2/5 power minus log base A of y to the 1/3 power. But I can't leave it like that because, first of all, these are both log base A's, which means I can combine them. In addition to that, we're just going to combine them. So we're going to get log base A of x to the 2/5 power divided by, because of the minus sign, divided by y to the 1/3 power. And the only other thing that, you possibly could do if you wanted to, is just rewrite it one more time as log base A of a root here. So x is here. So the 2/5, 5 being my little value in there, my root value, and 2 here, divided by y to the 1/2 power. Well, that's a square root, so there's a little 2 inside there. And so that would be equivalent to this value here. These are both the same. This one right here, we have a plus. That's a product rule. We have a minus. That's a quotient rule. You need to check to make sure that they're all log base A. So rewriting this, I get log base A of x to the 1/2 power. Plus means times. So I'm going to be multiplying that by y to the 4th power. And I'm going to be dividing that by, let's see here, x to the 3rd power. Oh, now in this case, this is kind of a little tricky problem because what we have is the same base. Now remember back when you were doing exponents or solving exponents or even simplifying exponents, and you had something like x to the 5th power divided by x to the 3rd power. And the rule for this is keep your base, subtract your exponents, right? Because if you're dividing, you subtract. So you have x to the 5 minus 3, right? And so in this case, you end up getting x to the 2nd power because you subtracted and you simplified. Well, the same case is for this problem right here. Okay, this is just an example. So see how I have the same base? I'm going to use this. See how I have x and I have an x down here? Well, we're going to keep the base, which is x, and I've got, I don't know if you can see that. So we have x to the 1/2 power minus the 3rd power. I'm going to multiply that and make that 2/2. So I have 1 minus 6. Well, 1 minus 6 is -5. So I actually have x to the -5/2 power. So I get log base A of x to the -5/2 power y to the fourth power. And the last thing that I would actually do is this right here. I mean, certain people want only positive exponents. So if that's the case, you would just do this. You'd say log base a of y to the fourth power over x to the negative 5 halves power. Oops, I'm sorry. When it moves to the bottom, it does become positive. And you could do that. I could also factor out some x's down there, but we'll save that for another day. Solving exponential equations. Now, this is just the beginning of solving equations, but let's just start. Obviously, I'm not going to get the same bases with 4s. So let's change this to a base 2. So see this 4? I'm going to change that to be 2 squared. And don't forget the 2x minus 1 already up there. This 8, I'm going to change to 2 to the third power. Also, see the x already up there. The bases are the same. I'm going to say 2 times 2x minus 1 is equal to 3x. And that makes 4x minus 2 equals 3x. Subtract 3, I get x equals 2. Okay. Remember that you can actually solve this with logarithms also. Let me just show you. Bringing this to the front, 2x minus 1, right? Bring that out of there, your variable out of the power out of there. So we would get 2x minus 1 as a parenthesis. Log 4 equals x log 8. I would most likely move these logs over together. So that would give me, simplifying, 2x minus 1 divided by x, I get x, equals log of 8 divided by log of 4. Please remember, do not cancel your logarithms. Do not simplify the numbers. These are quantities. And what ends up happening is, I believe, what do we get here? When you get a number here, log of base 10 of 8 divided by log base 10 of 4, and you get a number, and then you cross multiply, you're going to end up getting this value right here. It ends up becoming this when you cross multiply and divide. So we have 4x minus 2 equals 3x, divide. And so anyway, I'm going to end up getting x equals 2 on this side, but just an option that you can do that. For this one, we have only one logarithm. So we're going to go base to across the equal sign. So 3 to the second power equals 4x minus 7. 9 equals 4x minus 7. 4x is equal to 16. So x equals 4. And then for this problem right here, we have x to the second power, base to across equal sign equals 64. To get rid of this x squared, I'm actually going to square root both sides. Take this value to the 1/2 power, same as this, 1/2 power. So I get x equals, because these half powers cancel, 2 divided by 2 is gone. 64, if you don't have a calculator, you can rewrite 64 actually as, well, we know the answer is 8, but I'm going to show you a different way to do this. As 2 to the 6th power, don't forget this 1/2, so it's to the 1/2 power. Well, 2 divides into 6 3 times, I end up getting x equals 2 to the 3rd power, which is 8. So this problem can be a little bit tricky, because what we're going to do is we're going to pull this out front. We get 2x. And I'm going to use the natural log. 2x ln of v is equal to ln of 5. And the reason why I'm using the natural log is because I see the e there. And ln of 5. And in doing that, see this value here? Ln of v is just 1. So that's actually just 2x equals ln of 5. So x is equal to whatever ln of 5 divided by 2 is. And that is a number. It's written out here. I just don't have a calculator. So we start off, this is the same thing. It's just showing you step by step what you're doing. E to the 2x, which is here, is 5. we took the natural log of both sides, and we get ln of 5 divided by 2, and actually, here's my answer. So x is about 0.805. Okay. So just to review, our log properties is what the new stuff that we did today. If log base b of m is equal to log base b of n, then these two values have to be the same. Here's my properties. So here's the product rule right here. We did this. We then talked about and did some examples for the quotient rule. And we did some examples with the power rule. Do keep in mind, this is really, really important, that, sorry about that, bases and arguments. Now remember where the arguments are. The arguments, if I have log base b of, let's call it a for argument, is equal to x, then this is my base down here. See the little b? Bases and arguments. Here's my argument. Cannot be negative, ever. Okay, well, I hope that helped you, and I'll see you next time. Thanks, bye. Oops.